chair the last session of the day. Our next speaker is James Nakamura from Purdue University. He will talk about the evidence for anion statistics in the fractional quantum Hall regions through Fabry-Perot interferometry.
Okay, thank you. Can y'all see my screen and hear me?
Yeah, perfect.
Okay, great. Yeah, thanks for the introduction, and I want to thank the organizers for letting me talk at this nice conference. It's great we can get together and share our work. So I'll be talking about our group's work looking at anyonic statistics through electronic quantum Hall interferometers. And this is work I participated in the group of Professor Michael Manfra at Purdue University. So of course, this is a conference for experts. So I'll just briefly rehash the motivation for these experiments. So the fractional quantum Hall regime has garnered a lot of interest because it's expected to have these very exotic quasiparticles. The excited states of these fractional quantum Hall states are expected to carry a fraction of an electron's charge, so 1/3 of the electron's charge for the 1/3 state, for example. And then they're also expected to obey fractional or anyonic braiding statistics. And you can picture this as you take one quasiparticle and braid it in a loop around the other, and you'll get a Barry phase that's a fraction of 2 pi. So 2 pi times 1/3 is the theoretically expected value for the 1/3 state quasiparticles. And this braiding process in 2 dimensions is equivalent to swapping the quasiparticles' positions twice. So this can be seen as a form of statistics for the quasiparticles. Now, it's important to put our work today in context of the previous experiments that have been done, looking at these quasiparticles. So the quasiparticle fractional charge is something that was observed over 20 years ago now, originally through shot noise experiments, and first done at the 1/3 fractional quantum Hall state, and then extended to numerous other fractional states. So that's sort of the first indication of the experimental existence of these quasiparticles. And then interference experiments for fractional quantum Hall edge states have been done by several groups, with a lot of that work being pioneered by the Heiblum group at the Weizmann Institute for integer and fractional quantum Hall states, and several other groups have also worked in interferometry, including the Marcus group at Harvard. And there's some very interesting results from Bob Willett at Bell Labs showing evidence for interference at the possible non-abelian nu equals 5/2 state. And getting to some very recent experiments, as we heard about yesterday, there's observation of non-abelian anionic statistics through the half-integer thermal Hall conductance measurements, which we heard about in the talk yesterday. And again, these experiments at 5/2 are very important and compelling because of the possible application of non-abelian statistics to topological quantum computing. And again, getting to another very recent experiment just from early last year, which we heard about yesterday, is the observation of anionic statistics through quasiparticle collisions. So where our experiment that I'm going to talk about fits into all this is we have another way of observing anionic statistics, this time through a interference type experiment. So I'll discuss the type of experiment we're doing. We've fabricated the electronic equivalent of a Fabry-Perot interferometer using metal gates on the surface of our 2-dimensional electron gas to define the interference path, and quantum point contacts to act as beam splitters. So we'll take advantage of the fact that in the quantum Hall regime, current travels along the edge of the sample. So a current can come in from a source contact and be partially reflected by the first QPC, and then go through the device and be partially reflected by the second QPC, with the rest of the current going on to the drain. And now we have these 2 overlapping backscattered paths that can interfere. So the total backscattered current will, of course, depend on the individual tunneling amplitudes of the QPCs, but there'll also be a cross term that depends on the phase difference. And if these are just electrons at an integer quantum Hall state, for example, that phase will just be the Aharonov-Bohm phase of electrons moving in a high magnetic field. And so you can measure this phase or probe this interference by measuring the current or the conductance across the device. And then there are 2 ways to try to change this phase. You can change the area by changing the voltage on these gates to squeeze the area in more, or change the magnetic field directly with our superconducting magnet. And a key thing is that based on this phase being a product of area and magnetic field, if you do an experiment of changing gate voltage and magnetic field at the same time, what you'd expect to see are negatively sloped lines of constant phase or constant conductance. And this is some simulated data from theoretical work showing what you'd expect to see. So that's for integer states. And if we operate this at a fractional quantum Hall state, the phase should be modified in two ways. First of all, the Aharonov-Bohm part should be scaled by the quasiparticle charge because we're not interfering just electrons anymore. We should be interfering these fractionally charged quasiparticles. And then second, if there happen to be any quasiparticles localized inside our interferometer, our edge states of edge quasiparticles have braided around them, so we'll get a shift in phase due to the anyonic contribution. So this type of experiment should be sensitive to the fractional charge and statistics. Now, it turns out there's a problem with these type of experiments, which was seen early on, which is that, remember, our expectation is to see these negatively sloped lines of constant phase. But generally, if you just jump into these experiments, you'll see something strange, which is the opposite behavior, positively sloped lines of constant phase. And this was explained as being due to Coulomb charging effects, which give a bulk edge interaction that causes the area of the interferometer to change when you change a magnetic field. So some more simulated data here. There's a change in the interferometer area proportional to the change in magnetic field that gives this strange situation where you can have the magnetic flux decrease when you increase the magnetic field, and giving rise to this opposite from expected behavior. And the big problem for observing fractional statistics is it was shown that if you're in this regime of strong bulk edge coupling, in a device with strong Coulomb effects, then the anyonic phase will be unobservable. There's this close correspondence between phase and charge in the quantum Hall regime that makes that the case. So this is a problem that needs to be solved for this experiment to work. Now, in previous experiments, what was observed in small devices is always this positively sloped Coulomb-dominated behavior at integer quantum Hall states. But then what it was found is that if you put a large metal gate on top of your interferometer, you can recover the negatively sloped Aharonov-Bohm regime behavior. The problem with this is to get enough capacitance to the device to screen enough, this interferometer and this gate needed to be large. And the problem with large devices is you get poor phase coherence, and this interference was low amplitude and limited to low magnetic fields. So what was needed is a better way to screen these Coulomb effects in order to get interference in smaller devices. So our approach to solving this problem was to design a aluminum gallium arsenide heterostructure that builds the screening into the structure itself. So our structure has a main quantum well, but then additional screening wells, one above and one below the main quantum well, to replace the metal plate that was on the surface of the device and screen those Coulomb charging effects in the structure. So we designed this to have a short setback, 25 nanometers of the screening wells from the main quantum well, and to have a high density in the screening wells, and actually higher than in the main quantum well, to ensure good screening. Now, if you think much about quantum Hall measurements, you'll notice a problem with this, which is that we've, in this case, intentionally introduced a whole lot of parallel conduction into our structure through those screening wells, because they're going to be conductors as well. So to solve this problem, we've borrowed a technique from bilayer quantum Hall systems, which is to put metal gates. Here's an overview of our whole device. Metal gates going around the ohmic contacts, which we're going to negatively bias to selectively just deplete the screening wells. So we'll negatively bias the top one to deplete the top screening well and the bottom one to deplete the bottom screening well. And now our ohmic contacts are connected just to the main quantum well. So we probe just transport in the well that we're interested in seeing interference in. So to initially characterize that this works to suppress Coulomb effects, what we've done is operate our interferometer as a quantum dot at zero magnetic field and measured Coulomb blockade. So we're measuring here the differential conductance as a function of gate voltage and source drain bias. And you get this characteristic Coulomb diamond pattern, and from the height of that diamond, you can get the Coulomb charging energy. So for the device with the screening wells, this is a small energy, about 17 micro eV. And for a device with the same area, but on a standard structure with no screening wells, it's about a factor of 10 larger, 200 micro eV. So there's a pretty dramatic reduction of the Coulomb energy with these screening wells. Now, there's another possible advantage to using the screening well scheme, which is our collaborators have done simulations which show that in the screening well structure, the density profile at the edge of the gates, the confining potential, is significantly sharper in the screening well structure in the main quantum well than for a standard structure without the screening wells. And this is showing the density at the edge of the gates, and it's about 3 times of a sharper profile going from 0 to the full density than in the standard structure. And we also have some experimental indications this is actually the case, which is probing not the full interferometer, but just single quantum point contacts in the quantum Hall regime, measuring the conductance versus gate voltage. And this is for our screening well structure. You can see the conductance goes from the full E squared over H of the Hall conductance of the nu equals 1 edge state down to 0 very abruptly. Whereas for a standard structure without the screening wells, there's a much more gradual decrease from E squared over H to 0. So it's like in the standard structure, there's a much more gradual decrease in the density from 0 to the full density. And the reason, a qualitative way to understand why this is the case, why the screening well structure gets a sharper density, is that for the screening well structure, here's just a cartoon of this, the potential from the gate will be blocked everywhere except where the top screening well is depleted. So the main quantum well will only feel the gate potential in a sharply defined region around the gate. That's just a hand-wavy way, and the real thing to look at is the simulations. Now, the reason this sharp confining potential is an advantage is that it may prevent dephasing due to edge reconstruction. The High-Bloom group has shown that neutral modes that come about due to edge reconstruction can cause dephasing of quantum Hall interferometers. And as he mentioned this morning, a sharp edge, enhancing the sharpness of the edge can avoid edge reconstruction and get rid of those neutral modes, at least at some fractional quantum Hall states, such as 1/3. So that's the possible advantage we may have. So the real test is to operate our device as an interferometer in the quantum Hall regime. So we've done this first at the integer state nu equals 1, where we measured, done the experiment, measured conductance versus magnetic field and gate voltage. And you can see we have these negatively sloped lines of constant phase, constant conductance, which is indicative that we've gotten away from the Coulomb dominated regime and into the Aharonov-Bohm regime, which is where we want to be. So our screening wells really work. And what's great about this is in a small device with an area about 20 times smaller than what you'd be able to see this in just a gate with a top metal screening gate. And because the device is small, the interference is robust and large amplitude. The scale here is tens of kiloohms and survives up to pretty high temperatures of a few hundred millikelvin. So we have a previous paper reporting this result. So now we operate the device at the nu equals 1/3 fractional quantum Hall state and do the same experiment, measure conductance versus magnetic field and gate voltage. And you can see overall similar behavior, these negatively sloped lines of constant phase. But you can see now this is not a perfect interference pattern. There are some discrete jumps or glitches in the pattern here. And these jumps are intriguing to see because remember, we expect for a fractional state that the phase will be a combination of the Aharonov-Bohm part, which evolves continuously, but then also this anyonic contribution, which should change discretely when the number of localized quasiparticles changes. So to see what's going on here, we've tried to extract the value of the phase jumps by doing fits of an Aharonov-Bohm conductance pattern in each one of the regions between the jumps, with a fitting parameter being an offset phase theta naught, and then calculated delta theta as the difference in the fitted theta naught between each region. So when we calculate the delta theta, we find values are not all exactly the same. There's some scatter here, but if we take an average value, we found the average delta theta is minus 0.31 times 2 pi. Now, the theoretically predicted anyonic phase at the 1/3 state is 2 pi over 3. So it seems like we're kind of close in magnitude, but off by a sign. But actually, the expectation is you go up in magnetic field, you'll be removing the quasiparticles or equivalently adding quasi-holes. So that's where the negative sign comes from. So in fact, these phase jumps we see with this average value are close to what's expected for the nu equals 1/3 anyonic phase. So we take this as evidence that our interference experiment is sensitive to and seeing these the anyonic phase at the 1/3 state. Now, some more interesting analysis we can do is we can look at the fact that these phase jumps have a positively sloped trend in the magnetic field and gate voltage plane. They're kind of going against the grain of the Aharonov-Bohm part of the pattern. And this makes sense if these are quasi-particle transitions, because remember, the expectation is we go up in magnetic field, the quasi-particle should tend to be removed. But if you go up in gate voltage, electrostatically, that's going to favor adding more charge or adding quasi-particles. So those two things should give you a positive slope. And we actually, this is similar to what's been seen in resonant tunneling experiments, for example, in the quantum Hall regime, where there's a positive slope to the conductance resonances. And we can actually calculate what we'd expect the slope to be based on the parameters of our device. So doing a charge picture where the charge is a combination of this charge in the condensate, which varies with magnetic field, and then some fixed terms, and then the contribution from the gate voltage to charge in the bulk, the lever arm of the gate to the bulk. So we can put this and calculate the expected slope of these transitions, which we get a value of 0.44 millivolts per millitesla. And our observed value is close to that, about 0.5 millivolts per millitesla in the experiment. So there's that close agreement gives us some confidence that these discrete jumps in phase do indeed occur due to changes in localized quasi-particle number. Now, the data I've shown so far was from near the center of the nu equals 1/3 state, near the center of the conductance plateau in the bulk transport. But we also extended this to higher and lower magnetic fields. And when we do this, we see an interesting change in behavior where we go away from seeing this negative slope with a couple of discrete jumps, and the lines of constant phase seem to flatten out and become lower in amplitude. And so we need an explanation for this. And Bernd discussed this yesterday in his talk. Bernd Rosenau and Adi Stern came out with this theoretical work that may provide an explanation for what we're seeing. So I'll just rehash some of the important ideas and how they're relevant to our experiment. So they looked at the competition between the energy cost to create quasi-particles, basically the energy gap delta, and the electrostatic energy cost to avoid creating quasi-particles and keep the filling factor fixed. And they predicted a transition from seeing primarily the Aharonov-Bohm interference with 3 phynot due to the fractional charge Aharonov-Bohm period to seeing phynot period oscillations due to adding quasi-particles with a phynot period when you get to some critical magnetic field away from the center of the state. And this is sort of the zero temperature limit of that, as Bernd discussed. The idea is that in the middle, you're in the middle of the gap, go to low enough field and you'll be in the high density of states. And there should be a sort of particle hole conjugate to this, where if you go to high field, you'll be in the whole density of states region. And important for our experiment is they've derived an equation for how wide this region of fixed filling should be, where you see mainly the Aharonov-Bohm behavior. And it depends on a few parameters: filling factor, quasi-particle charge, and the capacitance per unit area. This basically determines how the energy moves as you change the magnetic field. And then, of course, the gap, which determines how far you need to move in order to start creating quasi-particles. So we can apply this to our experiment, and we can see in our experiment this finite region where the negative slope behavior occurs is about 450 millitesla. If we take the equation from their work and put in the parameters for our structure, the energy gap measured from transport, and the capacitance per unit area determined by our heterostructure we've grown, we calculate a value of about 530 millitesla. So there's a pretty good agreement between this theoretical answer and what we see in our experiment. So that gives us an indication that this theory does indeed describe what's going on in our device. So a question which Bernd addressed yesterday is why we don't see the phynot period oscillations, and it's due to the fact that we're at finite temperature. Instead, we seem to see this thing where the lines of constant phase flatten out, which makes some sense because you add one quasi-particle, and in this region, you'd expect to get one removal of what, add one flux quantum, you remove one quasi-particle or add one quasi-hole, and that cancels out the Aharonov-Bohm part. So no change in phase on average as you change the magnetic field, but you can still change the phase with by changing the Aharonov-Bohm part with the gates. And so you don't, and if you're at finite temperature, they showed that it's very these finite period oscillations you'd expect to get from the phase going up and down is very easily thermally smeared, which can be understood from the fact that when the density of states is high, the only thing keeping a large number of quasiparticles from flooding in and out is the charging energy, and that will effectively be very small because you have a small quasiparticle charge. Like the E star is small, and we have a large sort of self-capacitance because of all the screening we've introduced. So the E star squared over 2C will be a small value, and they predict a pretty small temperature scale of just a few millikelvin for the finite period oscillations that you might expect to see in these high and low field regions. So it makes sense that we don't see them in our experiment. So something that then bears some explanation is why we do see some discrete jumps in the center. And our understanding of this is that near the in a real device, the density of states is not going to be a perfect delta function. There's going to be some broadening due to disorder, so that there may be some quasiparticles that are lower in energy due to disorder. So as you sweep the field, you may see those transitions, and they don't thermally smear into the rest because they're isolated in energy due to the disorder potential. And this might explain why the discrete jumps we see are not evenly spaced. They're sort of a random spacing here, which could be due to disorder. So now a question is, if we could get the charging energy larger, that E star squared over 2C, maybe we'd have a chance of seeing the finite period oscillations in the high and low field region. So this is something we were interested in doing. So we made a significantly smaller device, area about half the size, but otherwise it's a similar type of interferometer. And we do the same experiment, measure conductance versus magnetic field and gate voltage. And in this device, overall the behavior is similar. You can see this negatively sloped behavior near the center of the state, and then lines of constant phase flatten out at high and low field. But now you can actually see some modulations here, some which turn out to have a period of close to finite. So in this smaller device, we've evidently gotten the charging energy large enough that those finite modulations can actually be seen. Then if we go to higher temperature, they quickly thermally smear out, and we see something similar to our previous data. And in this device, also near the center, you can see there are several discrete jumps in phase as well. And in this device, the average value is somewhat reduced from the previous device, about 0.24 rather than the value close to 1/3. And this discrepancy may be because we've gotten in this device the charging energy large enough that bulk edge interaction becomes important again, which was the thing we needed the screening wells to screen out. But in this device, we've gotten the charging pretty substantial so that there'll be a correction to the jumps in phase we see. So the correction predicted from theory is you'll see a change in phase equal to the anyonic part, but then there'll also be this part due to the bulk edge interaction, which is basically when a quasiparticle enters the area of the interferometer will shrink a little bit, so you'll get a shift in the Aharonov-Bohm part. So that may be what's going on in this device. So in conclusion, at the nu equals 1/3 state, we've observed discrete jumps in phase that have an average value close to the theoretically predicted value of 2π/3, so consistent with observation of anyonic statistics. And we also observe transitions in interference behavior when going away from the center of the 1/3 state. That's consistent with this theory developed by Bernd and Adi Stern. And in a significantly smaller device, we can actually see some of the finite period modulations. So these observations, we think the simplest explanation for our observations is we're observing the anyonic statistics of the 1/3 state. So this provides additional evidence on top of the previous experiments, which I mentioned earlier in the talk, the thermal Hall conductance and the anyonic collisions, further evidence for anyonic statistics in the fractional quantum Hall regime. So with that, I'll conclude my talk, and thank you all for your attention.
Thank you very much for the very nice talk. So we're still ahead of the schedule. So maybe we can have 1 or 2 quick questions. Oh, Bert, please go ahead.
Okay, well, it's just a comment, since there is time, just to repeat, it's actually just repeat. First of all, it was a beautiful talk, and the work is fantastic. Very, very exciting work. I just want to repeat something that a comment that I made, I guess after Bernd's talk, which is the fact is that in this regime where you're outside of the central region, where your B is, you're seeing now these, in the first sample, you just saw these horizontal stripes, and in the second sample at low enough temperature, you saw the additional 1/3, these additional phynot oscillations. One really should think about it in a more complicated way, because you have several different periods. Even though you're at finite, so in the first sample, you're at a high enough temperature, so you don't see the you don't see the phynot oscillations, but you do see the oscillations as a function of gate voltage, which says that you're not at such a high temperature that you can neglect the energy, the Coulomb formation energy. So but it's a much more complicated thing than just Coulomb energies. And one does predict, when you look at the detailed theory of what happens there, you do predict that there would be several different periods. The leading period is the one in which you have no phynot period, but do have an oscillation as a function of gate voltage. And then at lower temperatures, you get this competing period. And I would say that in some very crude sense, the one you do see is what corresponds to the Coulomb dominated, what you would predict for a Coulomb dominated phase, even though the Coulomb interactions are not playing such an important role there. And the AB period, which is what you see really only at the very lower temperatures, is the one with the phynot period. But it's weaker.
Yep.
Despite the fact that that for the integer case, you really have, despite the fact that the Coulomb coupling is weak, it turns out that at nu equals 1/3, what you predict is, even for very weak Coulomb coupling, you predict that you're going to see these Coulomb dominated like stripes.
Right, thank you for the comment. And I get my way of sort of understanding that is that the phase change for these quasiparticles, it's like the vortex encircling charge. So the phase has this direct correspondence to the encircled charge. So it resembles the Coulomb case.
I saw Song Yang raise the hand in a second. Song Yang, you can mute yourself.
Hi, hello. I have a question for James. It's actually from my friend Yang, who is watching through YouTube. He asked, in small devices, when average phase slips gets smaller, how about the period?
The period meaning the like Aharonov-Bohm period in the central region.
Yeah, I guess so.
So what it seems like is it's sort of the opposite. The Aharonov-Bohm period becomes slightly larger than the 3 phinots. So like there's no like perfect Aharonov-Bohm region because there's these discrete jumps, but the period seems to be somewhat larger than you'd expect, slightly larger than the 3 phinots. And I believe that's consistent with the influence of bulk edge coupling on that period as well.
I see. Thank you.
Andrea, do you have a quick question?
Yes. So this effect is due to the fact that some anyons enter the center region at a certain point. So do you have a way to control this, in the sense that you let more frequently or less frequently this anyon to enter the center region, such a way to make sure that what you see is indeed what you have in mind?
Well, for the moment, it seems that the spacing of these is just determined by disorder in our sample. Now we've been investigating some devices with extra gates, like a gate in the center of the device, in order to try to intentionally introduce them. And it seems it kind of works, although we've had some technical challenges with putting those gates in and introducing some extra charge noise. It's a little tricky because we have this screening wells as well, so there's a lot of charge that has to be depleted. But in principle, it can be done with additional gates.
Okay.
Thanks, James. So our next speaker is Smita